Transient response in RC series circuit having DC excitation. Let a DC voltage V be applied at t equals to 0 by closing the switch S in a series RC circuit. The current at t greater than 0 being I, application of KVL leads to Ri plus 1 by C integral of I dt equals to V. Differentiating this equation, we are going to get R di by dt plus I by C equals to 0. Now, this we can write as P plus 1 by RC of I equals to 0. That is equation 1. This is homogeneous differential equation whose solution will contain only complementary function. Particular function being 0, I equals to IC equals to constant of e to the power of minus t by RC. Let it be equation number 2. With the application of voltage and assuming no initial charges across the capacitor will not produce any voltage across it, but acts as a short circuit, causing the circuit current to be V by R at t equals to 0 plus I at 0 plus equals to V by R. Now, substituting these initial conditions in equation number 2, we are going to get the K equals to V by R. Now, finally, obtaining the current I equals to V by R e power minus t by RC. That is equation number 3. Now, it may be observed that the charging current is decaying function as shown here. With respect to time, the current is going to decay from initial value of V by R. As the capacitor is getting charged, the charging current dies out. The corresponding voltage drops across the resistor and the capacitor is given by VR equals to I into R, that equals to V by R e power minus t by RC multiplied by R. VR equals to V e power minus t by RC. This is equation number 4. And VC equals to 1 by C integral I dt, that equals to 1 by C integral V by R e to the power of minus t by RC dt. That equals to V 1 minus e to the power of minus t by RC. Equation number 5. Observing equation number 4 and 5, it reveals that VR is decaying function, VC is exponentially rising function. As shown here, with respect to t, this is voltage V, this is VR, and this is VC. The steady state voltage across the capacitor is V. The time constant is obtained by putting t equals to RC, which gives the VC equals to V of 1 minus e to the power of minus RC by RC, that equals to V of 1 minus 0.368, that equals to 0.632 V. That is the time by which the capacitor attains 63.2% of the steady state voltage. Here RC is the time constant. Now the instantaneous powers, that is P through R, is given by I VR, that equals to, from equation number 3, I is V by R e to the power of minus t by RC, and multiplied by VR equals to V from equation number 4 e to the power of minus t by RC. Then PR equals to V square R e to the power of minus 2 times t by RC in watts. Now, instantaneous power through capacitor is given by I into VC, that equals to I equals to V by R e to the power of minus t by RC, and VC is V of 1 minus e to the power of minus t by RC. Calculate this. V square by R of e to the power of minus t by RC minus e to the power of minus 2t by RC. This is PC. This is the case where switch is closed and the capacitor is charging. Case 2, discharging case, when the switch S is thrown from A to B such that RC circuit is short circuited and the voltage source is withdrawn. Now, applying KVL, then you are going to get Ri plus 1 by C integral I dt equals to 0. Now, differentiating, then you are going to get R di by dt plus I by C equals to 0. That is P plus 1 by RC equals to 0. That is equation number 6 and 7. This is the homogeneous differential equation, and its solution is only the complementary function, that is I equals to IC, that equals to constant K dash e to the power of minus T by RC. That will be equation number 8. However, at t equals to 0 plus, the voltage across the capacitor will start discharging the current through the resistor in opposite to the original current direction. Hence, the direction of current I during discharging is negative, and the magnitude is given by V by R. Thus, I at 0 plus equals to minus V by R. Then, the equation number 8 minus V by R equals to K dash e to the power of minus T is 0 divided by RC. Then K dash equals to minus V by R at T equals to 0 plus. Then the complete solution I is given by the K dash is minus V by R e to the power of minus T by RC. From this, the current decay transient in RC discharging can be drawn with respect to the time. This is the current I, the positive, negative, where this is the value of V by R. This is I discharging ID. Now the corresponding transient voltages, voltage across the resistor R, VR equals to IR, that equals to minus V by R e to the power of minus T by RC multiplied by R. Then VR equals to minus V e to the power of minus T by RC. And the voltage across the capacitor VC is given by 1 by C integral I dt. Now substituting the I value from this, you are going to get V e to the power of minus T by RC. Now obviously if you see this, VR plus VC equals to 0. And that can be represented with respect to time t, the positive voltage and the negative voltage here. VR is decaying as well as VC is decaying. In the discharging current, the time constant is given by the product of RC such that VC equals to V e to the power of minus T equals to RC by RC. That equals to V e to the power of minus 1, which is nothing but 0.368. We can write that VC equals to 0.37 V. The time by which the capacitor discharges to 37% of its initial value. Now the instantaneous power PR is given by VR into I, that equals to VR, that is minus V e to the power of minus T by RC multiplied by minus V by R e to the power of minus T by RC. That equals to V square by R e to the power of minus 2T by RC, which is PR. The instantaneous power in capacitor C is given by VC multiplied by I. VC is V e to the power of minus T by RC multiplied by minus V by R e to the power of minus T by RC, which equals to minus V square by R e to the power of minus 2 times of T by RC. This is PC, watts and watts. The charge stored in a capacitor during the charging is given by the Q equals to C VC, that equals to C V of 1 minus e to the power of minus T by RC from equation number 5. Then Q equals to CV is nothing but the charge Q of 1 minus e to the power of minus T by RC. While discharging, Q is given by C VC, that equals to C. Here for discharging, VC equals to V of e to the power of minus T by RC, that equals to Q, CV is nothing but e to the power of minus T by RC. Both are in coulombs. This is regarding the transient response in RC series circuit having DC excitation for charging and discharging cases. If this video is useful, please like, share and subscribe. Thank you.